Alright, so we talked about exponential growth. The next one we're going to talk about is logistic growth. With exponential growth, there were only two constants we had to worry about, making that problem a little bit easier. We definitely went a little bit more in depth in the exponential growth. We're not going to go nearly as far in depth with the logistic growth models. This is your general equation for logistic growth. I wouldn't say it's super important to memorize this one, but essentially we have the same values. X and Y are still your variables. X is usually an amount of time in, and then Y is usually a total amount of something. And what we still have here is now we have three constants. We have a constant on the top of the fraction, we have a constant in front of E, and we also have a constant that's in front of X, similar to before. When you're talking about logistic growth usually has a characteristic of it starts growing very slowly, and it ends by growing very slowly, and then in the middle there is this portion of rapid growth, kind of circled here in blue, where the growth is happening the fastest. That's what the characteristic of logistic growth is. So here we have, on a college campus, 5,000 students. One student came down with a contagious flu. The spread of the virus is modeled by, and it gives you this is technically a logistic growth model right here, where Y is the total number infected after T days. Well, a very straightforward question is how many students are infected after 5 days. Well, if we think about it, this gives us, Y gives us our total infected, and T gives us the number of days. So if they tell us 5 days have passed, well, what do we need to take 5, and I hope you see that we need to substitute 5 right there for T. The rest is a calculator exercise. Y equals 5,000 over 1 plus 4,999 e to the negative 0.8 times 5. So this is going to be a lot of calculator work. So hopefully you can see how I'm using the calculator here. So I like to do the order of operations first. I'm actually going to do the negative 0.8 times 5 because that's the first thing I would do. Now I know I have to raise e to that power. So that's e to the negative 4. Whether you type it in or use the answer key doesn't matter. I'm still not done. I need to multiply that times 4,999. Hit enter. Still need to add 1. That's still on the bottom. And when I'm done, I take 5,000 and I divide it by my answer. Notice, I have done that whole exercise never rounding. I used exact values. I mean, the calculator rounds after 8 or 9 decimal places, but I never rounded to 2 decimal places because that actually will affect your answer. So you can say with confidence that after 5 days, 54 people are infected. 54. I hope you can't have 0.01 of a person. That might be a little strange. Okay, so anyway, last part here would be, when will 40% of the campus be infected? And we're still using that same equation, but what I want to stress is 40%. Well, what is 40% of 5,000? Well, 10% is 500, so 40% would be, when are 2,000 people affected? So if you're going to solve this, this is going to be the same exact equation. You're going to have, but this time they've given you a Y value, and they want you to solve for 1 plus 4,999 e to the negative 0.8 t. They want you to solve for t. This button doesn't seem to be working today. All right, here we go. They want us to solve for t. Well, right off the bat, I see t's in the denominator, so I don't want it there. I need to get t out of the denominator, so I'm going to multiply by 1 plus 4,999 e to the negative 0.8 t. I'm going to do that to both sides. 1 plus 4,999 e to the negative 0.8 t. That needs parentheses because we're about to do the distributive property. So here, I can cancel out. And I'm going to have 2,000, because I just did the distributive property. 1 times 2,000 is 2,000. Plus, I'm going to need a calculator for this one. 4,999 times 2,000. That's going to be 9,998,000. 9,998,000 e to the negative 0.8t equals 5,000 still remains. Well, your strategy from here is the same strategy we've done many times over. When you have to solve using logs, we're going to need to put it in log form. Now we're almost in log form. I have 9,998,000 e to the negative 0.8t equals 3,000. I need to divide by this big large number, 9,998,000. 9,998,000. And then I'll be able to put it into log form. So what I have here is e to the negative 0.8t equals, I'm going to need a calculator again. Let's do 3,000 divided by 9,998,000. Enter. So I've got this very small number, all right? It looks like it's, if I put it from scientific notation, that's moving the decimal place 1, 2, 3, 4, 5 times. That's the number in scientific notation. Well, now I got to put this into log form. Well, this is going to be log base e, which is ln, 0.00003 equals negative 0.8t. So to solve this, it's just going to be take this answer and divide by negative 0.8. So the rest is calculator work from here. All I have to do is take the ln of that long number that I just had in the calculator. So I'm actually going to use second answer, so I don't have to type it over. And that means even if I didn't do the scientific notation correctly, I still have the correct number in the calculator. So we hit enter to start, and then I have to still divide it by negative 0.8, and I hit enter, and it's going to say 13 days in, this flu is going to be wreaking havoc. I think that was 13 point what? All right, and for our final problem of the day, we're going to talk about the Richter scale. I'm sure you may have heard of this. I'm sure if you lived in California, you've heard of this. But the Richter scale is used to measure earthquakes. And what the Richter scale does is you've heard of these numbers on the Richter scale. Oh, that hurricane was only a 3 on the Richter scale. I'm sorry, that earthquake was only a 3 on the Richter scale. That wasn't too bad. Oh, that hurricane was a 6 or 7. That's much more intense. Well, this is the score, the Richter score right here. That's the actual Richter score, and what we have here is this level, this value I is called the intensity. All right, and the original intensity, that's what I sub 0 stands for. I sub 0, the original intensity is 1, so this is always going to be a 1 in this statement. So what we're going to use is we're going to use the Richter scale to figure out the intensity, because if you know the Richter score, you can figure out the intensity of the earthquake. So 2 earthquakes, if you had one in Peru that, let's say, measured 8.4, and you had Mexico, an earthquake that was 7.6, find the intensity of each. So I know those scores look very close, but let's see how closely their intensity is measured. So we would have the Richter score is equal to the log of the intensity over, well, the bottom's always, this is a 1, not an I. So that bottom, the original intensity is always 1. So let's do Peru first. All right, Peru, we know had a Richter score of 8.4 is equal to the log of I. And the question is, how can I solve for I? Well, because it's a log, I know the base is 10. So let's rewrite it in exponential form. 10 to the 8.4 is equal to I. Well, that's a straightforward calculator pushing, button pushing. 10 to the 8.4 comes out to, the intensity in Peru was, let's see, 643. So that comes out to 251,188,643. Let's check out the intensity in Mexico, which is the same exact work. So this is Mexico. It's the same exact work. I think of my log base 10. I do 10 to to the 7.6 is going to get me the intensity in Mexico. And again, that's pretty straightforward. 10 to the 7.6. That comes out to be only 30. I mean, comparatively, this one was 251 million in terms of a registered intensity. This intensity registers only 39,810,717, 718 if you want to be super precise. So even though their Richter scores were actually very close, the Richter scale 1 on the Richter scale actually is a 10 times more powerful earthquake just by going up 1 unit on the Richter scale. So anyway, I'm sure we'll see some Richter problems on our assignment in class. I look forward to seeing you tomorrow. Enjoy the rest of your day.